Implicit differentiation. We're going to go ahead and remember that this symbol d dx is an operator that instructs you to take the derivative and treat x as the variable. So d dy is an operator that instructs you to take the derivative and this time treat y as the variable. So keep that in mind as we take a look at the next example. In this example, we want to find each derivative treating y as a function of x. So in other words, y is equal to f of x. So here we have take the derivative with respect to x of 3y squared. So here notice that the variables don't match, but we were told to treat y as a function of x. So another way to think about this problem is take the derivative with respect to x of 3 times f of x as a quantity squared. So now I can think about this problem as a chain rule. So if I take the derivative of this, bring that 2 to the front, so I'm going to get 6, leave the inside the same, f of x, times the derivative of the inside, we're going to get just generically f prime of x. So now this looks a little messy. We'll go ahead and clean it up to look like 6, and we said f of x was equal to y, so 6y, and then f prime of x, so we have a couple different ways of writing this. So f prime of x, we can write it as y prime, or we can write it as dy dx. So we're going to go ahead in this case and choose to write it as 6y dy dx. So now I want to go back and look at the original problem. Take the derivative with respect to x of 3y squared. So our answer ended up being 6y, which is like taking the derivative sort of as usual here with the power rule. So we get 6y. But then we had to go ahead and tack on a dy dx. So take the derivative of that inside piece y with respect to that variable x. So this is a very basic example of implicit differentiation. Let's go ahead and take a look at the next problem. I have take the derivative with respect to x of 3x squared. So since the variables here match, we don't have a problem. Essentially, it's just 6x. So we've done the power rule before, and the only difference here is these are the same variables. So we get just 6x. And if we thought about this as the chain rule, the derivative of the inside, the derivative of that x, is just 1, because it's kind of like doing dx over dx. Take the derivative of x with respect to x, and dx over dx is 1. So it's just 6x. And taking a look at the next one, the derivative with respect to y of 3y squared, since they're the same variable, again, it's just the derivative sort of as usual. We get 6y. So we don't have to include that additional piece because the variables did match. So in this last example, we have take the derivative with respect to y of 3x squared. So here the variables don't match. And so what we're going to do is we're essentially going to treat it like the first problem. The derivative of 3x squared, we're basically going to take the derivative sort of as usual. We're going to get 6x. But since the variables didn't match, we have to use the chain rule. So we have to say, okay, well, the derivative of that inside function, that x, would be dx dy. So we have to remember to take the derivative of the inside, which is just x, the derivative of x with respect to y. So this is going to be our answer for the last problem. Now let's define an explicit function, which is a function in which the dependent variable can be written explicitly in terms of the independent variable. So for example, y equals f of x. So these are the types of functions that we've dealt with in the past. So this example, given y equals 3x squared minus 2x plus 1, find y prime. So since y is on one side of the equation and the variable x is completely on the other side of the equation, this is an explicit function, and to take its derivative, well, we just get y prime on the left On the right, it's just the power rule each time, 6x minus 2. So these are the types of functions we dealt with in the past, explicit functions. Now let's define an implicit function or relation. A function or relation in which the dependent variable is not isolated on one side of the equation. So for example, the equation x squared plus y squared equals 1 represents an implicit relation, specifically a circle. So we have the x variable and the y variable on the same side of the equation so that y is not isolated on one side. So this is an implicit relation that we have. And specifically, again, it's a circle. So how would we find the derivative of something like this? So in this example, x squared plus y squared equals 1, find dy dx. So what we're going to do is we're going to take the derivative with respect to x on both sides of the equation. So since we want the derivative of y, essentially, with respect to x, we need to take d dx of both sides. So d dx of x squared plus y squared, and then d dx of 1. So on this left-hand side, the derivative with respect to x of x squared, well, since those variables match, we just get a 2x on the left, the first part of the left, and then the derivative with respect to x of y squared, so since those variables don't match, we're going to take the derivative sort of as usual with the power rule, 2y. And then the derivative of the inside, the derivative of y, is dy dx. And then the derivative with respect to x of a constant is just 0. So now I want dy dx, so I'm going to isolate it by subtracting 2x and dividing by 2y. So dy dx is equal to, if I subtract the 2x and divide by 2y, I end up with negative x over y. So we just found dy dx is negative x over y. Notice what's different from our previous derivatives is that there are two variables in the answer. But this derivative still is the slope of the tangent line at any point. But now we need both an x value and a y value to find numerical derivatives. So on the circle, for example, if I wanted the slope of the tangent line at, let's say, x equals 1/2, I would also need the corresponding y value at that point in order to find the slope of the tangent line at the x value 1/2. So here, since we're on the unit circle, we know that if the x value is 1/2, then that does correspond with the y value, radical 3 over 2. So if we wanted the slope of the tangent line, we would simply plug in the x value of 1/2. So right here, the slope would be negative 1/2 over positive radical 3 over 2. So because the formula for the derivative was negative x over y. So if we simplify this, it's negative 1 over radical 3. So that would be the slope of the tangent line at the point 1/2 radical 3 over 2. So note that we can solve the implicit equation that x squared plus y squared equals 1 for y to arrive at the two explicit functions, so we'd get plus or minus the square root of 1 minus x squared to represent the top and bottom of the unit circle respectively. So we can rewrite the top as positive radical 1 minus x squared and the bottom of the circle to be negative radical 1 minus x squared, so that we really do have functions. So the top part of the circle would be a function, the bottom part of the circle would be a function. But some equations cannot easily be written as one or more explicit functions. So thus we need to use this method of implicit differentiation. In this next example, we want to find the derivative of y with respect to t. So given y to the 4th minus y equals t cubed plus t. So we're going to start by taking the derivative with respect to t of both sides. And on the left-hand side, we have variables that don't match. So when we take the derivative of y to the fourth, we're going to get 4y cubed dy dt minus, and here the derivative of y would just be 1, and then with the chain rule we're going to get another dy dt out. The derivative of t cubed with respect to t is just 3t squared and then plus 1. And now we want to isolate dy dt, so we need to factor it out of both terms here. So dy dt is factored out, and what we have left is 4y cubed minus 1 equals 3t squared plus 1, making the final answer, dy dt, equal to 3t squared plus 1 over 4y cubed minus 1. So there is my derivative, my dy dt. This next example has a few parts. So part A, find dy dx, given x cubed plus y cubed equals 6xy. So we're going to start by taking d dx of both sides of x cubed plus y cubed on the left and d dx of 6xy on the right. So on the left hand side, the derivative of x cubed is 3x squared plus the derivative of y cubed is 3y squared, and then we have to include dy dx. So we took the derivative of the inside, dy dx. Now on the right hand side, we have a product rule. So 6x is one function and y is a separate function. So we have to use a product rule in this case. So we're going to have the first function, 6x, times the derivative of y, well that's going to be dy dx, plus the second function y, and we're not taking its derivative, so we don't put a dy dx, times the derivative of 6x, which is just 6. So in this problem I have dy dx's on different sides of the equation after differentiating, so I have to move them around, get them to one side of the equation, and to be able to isolate my dy dx. So I'm going to keep the dy dx's on the left, so I'm going to keep the 3y squared dy dx on the left. I'm going to subtract 6x dy dx, and there's a 6y on the right hand side, and I'm going to subtract over the 3x squared. So now that I have my like terms on one side of the equation that involve dy dx, I can factor that out, and I'm left with 3y squared minus 6x equals 6y minus 3x squared. So I'm going to divide now to get dy dx by itself. So dy dx equals 6y minus 3x squared over 3y squared minus 6x. And it's important to note that we could have an answer that looks really similar to this that is correct, and what's really happening is we're just moving the negative around in the problem. So an exact same answer would be in the numerator to have a positive 3x squared minus 6y over in the denominator writing 6x minus 3y squared. So if you notice, just all the terms have the opposite sign because it's like factoring out a negative and throwing it to the denominator. So both of these are correct answers. For part B, we want to find an equation of the tangent line to the curve at 3, 3. So an equation of the tangent line means that we need to find a point and the slope. So the point is given as 3, 3. Here was our dy dx from part A, so we need the slope at dy dx, so the slope at 3, 3. So if we plug a 3 into each variable here for x and y, we are going to end up with 27 minus 18 over 18 minus 27 or 9 over negative 9. So we have a numerical slope of negative 1. So at the point 3, 3, so here's that point 3, 3, I can see that the slope looks like it's about negative 1. So that's what we just verified here. So we don't want just the slope of the tangent line, then we'd be done. We want an equation of the tangent line. So we're going to use our y minus y1. So this is our coordinate point 3, 3, equals our slope m, negative 1, times x minus 3. So that's in point slope form. If we want to put it in slope intercept form, we're going to end up with negative x plus 6 as our equation of the tangent line. And we can see that if we extended this line, that we would hit a y-intercept of 6 with that slope of negative 1. So here is my slope-intercept version of the equation of the tangent line. And finally, for part C, we're asked at what point in the first quadrant is the tangent line horizontal? So if we take a look at our curve, we want to know where in quadrant 1 over here we have a horizontal tangent line. So we can see that it happens right about there. So we're looking for that coordinate point where I have a horizontal tangent line. So once again, here's my dy dx, and if I want to know where the tangent line is horizontal, I need the derivative, the slope of the tangent line, to equal 0. So I need to set my derivative, 3x squared minus 6y over 6x minus 3y squared, equal to 0. So if I multiply by this whole denominator, I mean essentially to set something equal to 0 that is a fraction, it's just setting the numerator equal to 0. So 0 equals 3x squared minus 6y. Or we end up with the relationship 6y equals 3x squared, or y equals x squared over 2. So whenever the y value equals x squared over 2, that's where my tangent line is horizontal. And that's where we take this equation and we substitute it into the original equation. So we're going to go ahead and in the original equation substitute in our x squared over 2 into every y. And when we do that, we're going to end up with x cubed plus we're going to have x to the 6th over 8 and then 3x cubed. So if we go ahead and write x to the 6th over 8, and if I subtract the 3x cubed to the left-hand side, I'm going to have a negative 2x cubed equals 0. If I want to clear fractions here, I get x to the 6th, so I'm multiplying everything by an 8, I get 16x cubed equals 0. So factoring out an x cubed, I get x cubed minus 16 equals 0. So I end up with, really this is broken down into two separate parts, x cubed equal to 0, and x cubed minus 16 is equal to 0. So x cubed equals 16, or x is the cube root of 16. So we have two values, 0 and the cube root of 16. We wanted to know the value in quadrant 1. So at 0, 0, I can see I have a horizontal tangent line, but that's not in a quadrant. So that means I'm looking for the cube root of 16 as the x value of my coordinate point, right? So it's asking at what point. And then I need the y value. Well, way back over here, I had y equals x squared over 2. So now I'm essentially just going to plug in the cube root of 16 into this x to find the y value. So we end up with, in this case, 16 to the 2/3 over 2. So I'm plugging the cube root in. That's the fractional exponent 1/3. So I'm multiplying the 2 and 1/3 there. So I'm just going to leave my answer like this. So the cube root of 16, comma, and then 16 to the 2/3, or the cube root of 16 squared over 2. So this is the point in quadrant 1 where the tangent line is horizontal. In this next example, I want to find dy dx given sine of x squared y plus x squared equals 3x minus cotangent to y squared. So we're going to start by taking d dx of both sides and giving ourselves plenty of room on this one to find the derivative of each side with respect to x. So on this left-hand side, I'm going to have a chain rule. So I have sine of x squared times y. So inside of it is going to end up being a product rule. So we're going to have the derivative of sine is cosine. We leave the inside the same, so x squared y, times the derivative of the inside, and that's where I have a product rule. So I have the first function x squared times the derivative of y, well that's dy dx, plus the second function y times the derivative of x squared, which is 2x. Now that was just the derivative of sine of x squared y, plus the derivative of x squared is plus 2x, and then equals on the right hand side, I'm going to have just a constant 3. And then here, the derivative of cotangent is negative cosecant squared. So that negative and that negative are going to cancel. So we have plus cosecant squared of the inside, 2y squared, times the derivative of the inside, 4y dy dx. So we need that dy dx there when taking the derivative of this inside. All right, so now we have to, on this left-hand side, we have to distribute in this whole quantity. So I have this cosine x squared y quantity that we're going to have to distribute to each of these pieces here so that we have all of our terms added or subtracted so that we can gather like terms on each side of the equation. So when we distribute this, we're going to write it as that x squared, this x squared goes in the front, cosine x squared y dy dx. Remember, you cannot put x squared inside the cosine function. Can't take anything and put it inside or pull anything out of a trig function. And then plus this 2xy, we're just going to keep it on the outside and multiply it by cosine of x squared y plus 2x, so that's that 2x right there. And then this left side is fine, so we have 3 plus, I'm going to go ahead and bring that 4y to the front, cosecant squared of 2y squared dy dx. And now we can gather the two terms with dy dx is on one side of the equation, so we'll have x squared cosine x squared y dy dx is already on the left. We'll subtract 4y cosecant squared 2y squared dy dx, move it to the left. And on the right, keep the 3, subtract the 2x quantity, and subtract the 2xy cosine x squared y. And then we can, on the left-hand side, factor out our dy dx. So I'm going to go ahead and do this all in one step here. I'm going to factor out the dy dx on the left-hand side. So dy dx is going to equal the entire quantity on the right-hand side, 3 minus 2x minus 2xy cosine of x squared y, all divided by the part that's left over after factoring out dy dx, which is my x squared cosine x squared y minus 4y cosecant squared 2y squared. So these implicit differentiation problems can obviously have some messy answers. So this is my derivative dy dx. In this example, we have find the second derivative with respect to x given 3y squared minus x equals x squared minus y. So we need to start by taking the first derivative. So we're going to take d dx of both sides, d dx of 3y squared minus x, and d dx of x squared minus y. So fairly straightforward in terms of implicit differentiation here. We're going to end up with 6y dy dx minus 1 equals 2x minus dy dx. We'll go ahead and add the dy dx to the left-hand side, so 6y dy dx plus dy dx is equal to 2x plus 1. And all at once here, I'm going to go ahead and say, well, dy dx is then equal to 2x plus 1. And if I factored out the dy dx on the left-hand side, remember there'd be a 1 here, so I'd be left with 6y plus 1 as the quantity I would be dividing over. So here's my first derivative. Now the question is, how do I get to the second derivative? Well, I would differentiate this quotient. So I would need the quotient rule here. So my second derivative is going to end up looking like, so my second derivative is going to be the quotient rule here. So we have the bottom function, 6y plus 1. The derivative of the top is 2, so low d high, minus 2x plus 1 high, d low. So the derivative of 6y plus 1 is 6 dy dx. And then all over low squared, so 6y plus 1 squared. And on these problems, there's basically just a little bit of a substitution trick. I guess I don't want to call it trick, it's just a substitution. I don't want to leave dy dx in my answer. So I actually already have a quantity for dy dx in terms of x and y. So I have dy dx is 2x plus 1 over 6y plus 1. So I can go ahead and substitute that into dy dx. So I'm going to write this for now as 2 times 6y plus 1 minus 6 times 2x plus 1. And then I'm replacing this dy dx with 2x plus 1 over 6y plus 1. And then all over 6y plus 1 squared. And this is the second derivative, so at this point it's just a matter of simplifying here. So what we can go ahead and do is in the numerator, I can go ahead and multiply this 6y plus 1 by another copy of 6y plus 1 to have common denominators up here. So in other words, I have 2 times 6y plus 1 squared minus 6 times 2x plus 1 squared. That's these two copies together. So now this whole thing is all over 6y plus 1, but then that whole thing is all over 6y plus 1 squared. So I can rewrite this as 2 times 6y plus 1 squared minus 6 times 2x plus 1 squared all over the 3 copies 6y plus 1 cubed. If I think about multiplying by the reciprocal, this is what I'm going to have as my final answer for the second derivative using implicit differentiation. So the real big piece here is that substitution of dy dx back in from the first piece of the problem.